Now we've talked about some sources of magnetic field. We should talk about what it actually does, why we bother with this. And it turns out magnetic fields exert forces on charges, but in sort of a weird way. Experimentally, it's been found. This is generally easily confirmed now by taking a cathode ray tube and getting a stream of electrons, which are negatively charged particles, and just running it through some standard fields created by, say, current, and you see the following weird effects. A particle at rest suffers no magnetic field no matter how strong the magnetic field is. That's weird. Second, there's no magnetic force on a particle if it's moving, as long as it's moving parallel to the magnetic field. So that's a little strange too, that if the particle is moving in the direction the field is pointing, here we've got the field in the plane, we're moving the particle in the plane, then it turns out experimentally there's no force. Not shown here, but also equally true, there's no magnetic force on a neutral particle. So magnetic fields do act on charges. You need to have a charge, but they don't act on neutral things. It turns out that the force that is exerted is perpendicular to both the magnetic field and the velocity. So if we have the velocity in some plane and the magnetic field in that plane but a different direction, then there will be some force and it will be out of the plane. It'll be maximized when the angle is 90, when the magnetic field is perpendicular to the velocity, and it will be 0 when they're aligned, as we said before. In vector algebra, we capture this by something called the scalar, or the cross product, or the vector product, where we have that the force is the charge times the velocity crossed into the magnetic field. And we'd read this as QV cross B, as just like it looks like. We're not going to use a lot with the vector notation directly, but it's worth to use it, thinking of it as a shorthand for the idea that the force is perpendicular to both V and B, because the cross product of two vectors is defined to be perpendicular to the two of them, given by the right-hand rule, which we'll talk about in a little bit. In magnitude, the force is the size of the charge times the speed times the magnitude of the magnetic field times sine of the angle between them, where theta is as you would expect. If that's the B field and that's the velocity, then theta is that angle. All right, the directions are again given by a right-hand rule. Your textbook likes to say thumbs along V, index finger along B, and your middle finger will point along F, as illustrated down here. I learned it, and will probably continue to refer to it as index finger along V, middle finger along B, and your thumb will point along F. But either is fine, and in fact, as long as you have a cyclical permutation, it works fine. So it's either index finger and then middle finger and then thumb, but you can rotate these and say cyclically, like say this way. So we could also say that the thumb and then the index and then your middle finger will point along what you want. Or you could rotate it again, I suppose, and say middle finger to thumb, and then your index will point along the thing you want. It doesn't really matter because you can prove in vector algebra that they rotate cyclically, so it doesn't matter which one you call as your original direction, as long as you're consistent. And as long as you use your right hand. A silly but common error for students is to work all these things out, but forget to put down their pen, so they're working with the left hand, and they get the sign wrong. So use your right hand, or remember, use your left hand, but swap the sign at the end. All right, so an electron moves through a magnetic field as shown. In what direction is the electron accelerated? Well, if we sort of sketch this out again, we have V pointing that way, and we have B pointing that way. So one into the other, all right, like that gives us that this is coming, trying to show it here, out of the board, out of the page. On the other hand, we have to be careful because the force is not V cross B, but Q times V cross B. So if V cross B is out of the page, but it's an electron with a negative charge, then the actual final answer would have to be into the page. All right, proton moves rightward above a long right wire carrying current to the right. What direction is the magnetic force on the proton? Well, we remember that a long straight current produces a field which is circular. So, and we put our thumb along the direction of the current, and our fingers curl, and we would see that that's like this. So there's circles like that. And at the location where the particle is, it would be tangent to that circle, but coming out of the board. So now we have a velocity which is rightward, and a magnetic field which is coming out of the board. So sort of imagine that as out of the board. And then that means that the cross product would be downward. This is V cross B. And then since it's a proton, we know this the force is in the same direction as V cross B, so it must also be downward. Here are some artist-rendered interpretations as opposed to my little scrawlings there. All right, consider a charged particle moving perpendicular to a uniform magnetic field. The force on that particle is perpendicular to its motion always, but the acceleration then is perpendicular to the motion and is constant, which is the recipe for uniform circular motion. All right, we have a constant force that's always directed towards some point. Or in this case, it's always perpendicular to our velocity, but that would mean circular motion. And so, therefore, we end up in the same place. Let's investigate a little further. The magnetic force must provide the centrifugal acceleration. So we have that the magnitude of the magnetic force is Fc. Magnitude, remember, is QVB. There's also a sine theta in here, but we've arranged to have it perpendicular, so sine theta is 1. So we have QVB equals mv squared over r. So we could find the radius by saying it's mv over QB. Obviously, we need the absolute value bar to make sure this is positive, but we can see that the effect of having an opposite sign would be to have a circle of the same size but opposite handedness, opposite direction. Notice that we get the momentum over QB. That's an interesting thing that comes out that survives in relativity. Even when we lose that P is mv, we do get that the momentum over QB is still valid, which is interesting and neat. It's interesting that the mass-charge ratio is the important driver here. Think for a moment, what about a particle whose velocity is not perpendicular to the uniform B field? So it's moving, but not necessarily perpendicular to the magnetic field. What sort of path does it take? Well, the component parallel to the field is unchanged because there's no force that will go there. Right? There's no force of motion along lines because we know that that component crossed into B is 0, so the force in that direction is 0, so there's no change in its motion. The perpendicular component swings around in a circle, which tracks out what's called a helix, the thing shown here on the right. We also say it's undergoing helical motion. We often say that the charged particle is pinned to the magnetic field line. It's trapped. It spirals around the field lines. And the stronger the magnetic field, sort of the tighter its radius, and the more likely it's following sort of one line. Remember, this is kind of fuzzy because field lines are actually just mental concepts, but it's pretty close to true. And it's certainly useful whether or not it's strictly true. For example, the magnetic field of the sun can be mapped because the plasma, which is simply a charged gas, is trapped and spirals along the field lines. So we can see it glowing, and we can see where it goes, and we can kind of see the magnetic field lines even coming off this thing, coming off the sun. It's a little more complicated than that sounds like because, of course, the plasma being charged particles, they react to the field, but since they're moving charged particles, they are currents, so they also generate magnetic field. So the magnetic environment of the sun is, as you might expect, kind of complicated and weird and extraordinarily complex to actually understand, but in its broad outlines is pretty simply just particles trapped on these magnetic field lines generated by the rest of the plasma. All right, an important device in the history of science is something called the cyclotron, originally invented to study fundamental particle physics, now also used medically to generate radioactive isotopes needed for some medical imaging. The particles are accelerated across the gap by the large potential. What we have here is a magnet that's in two sort of semicircular regions. They're just strong permanent magnets. And then there's some potential difference across them maintained by some source, some EMF source. And the idea is that when the particle, say a proton, is injected into the magnet, it goes around the magnet, losing and gaining no energy. But then it comes to the potential gap, which is rigged to make it accelerate, so it picks up some extra energy. That means that it moves outward in its location because R has gone up. Remember, R is mv over qb. We've just added the v, so R gets a little bit bigger. But if we look at the period, right, the period of oscillation, of rotation here, is, of course, going to be 2 pi R over v. And remember that R was mv over qb over v. And so we see we get like 2 pi m over qb, and we get that it's independent of velocity. No matter how fast this thing is going, they have the same, it takes the same amount of time to do one full circle, or maybe more importantly, one half circle. So as a particle moves around, it picks up a little energy, it moves out, and then half a period later, which we know exactly because of this, we flip the sign of the potential and it picks up another kick. So it's a little faster and goes around, and then it's kicked again, and it's basically going to spiral outward every time kicking, the kick giving a little bit more energy. It's going a little faster, and eventually we get to where we need to use it, or we can't hold it in or whatever, and it comes off tangent, and then we can use that beam of protons at whatever our target is. All right, circle in blue the cases where the particle is positive, and circle in red the cases where the particle is negative. Let's look at case A. V cross B, we have something which is out of, well, we have this thing is going this way, and B is into, so if I sort of want to draw it here, B is into the board, so QV cross B, QV cross B points this way. This is V cross B. But we know, of course, the force had better point the other way. The force had better point in to get centripetal motion, and therefore this would have to be a case where we had negative charge. Have negative charge so as to flip this sign around. All right, well, we can see that V is going the exact opposite way, so that would have introduced a minus sign, which means that B cross V is into the board, or into the center there. That's the direction we already want it to be, so we should leave it as a positive charge. And then case C is like case A, but we flipped both things, so we know we're going to the same place. Whoops. And case D is like case B, except we flipped both things, so we'll end up no change in sign.